what I want to do is actually get an optimizer plugged in and watch our timeout circuits. And then go in and check the voltage reading. Now, the optimizer is not plugged in, so to speak. I have the power feed here not connected, which is the same as the key off once it's wired up to the vehicle. And I'm checking the resistance on one of the coolant circuits. This is essentially that parallel resistor that jumpers across our sensor. This is how much resistance we're adding in parallel. And we can see it's 9.90. Now what I'm going to do is I'm going to hook up this lead. Two things to note. First of all, you'll hear a click. That's the board mount relay that's going to reconnect our keep alive memory. The second thing to note is this will jump from 9.9 probably to about 10.8 k ohms. All right? Digital pots have a rest position. The rest position for this one is 9.9 k ohms. Once power is fed in there, then the microprocessor takes over. And it will start it at position number 1, which is the full maximum value of the digital potentiometer, full resistance value. So watch those two things. Listening? Hear the click?
Yeah.
And where do we go? About 10.3 k ohms. And it should be timing out. I'll be a son of a gun, it's not timing out. I wonder if this was a bad optimizer. You know what? Let's try a different circuit. There's green, I think blue was one.
Maybe that's the glitch.
No, this is not the one that we just received. So, okay, that goes 9.82. We hook up power. 1014, not timing out. We got a bad map.
Yeah, it is. It's going down.
Oh, 10,
The other
oh
one
wait,
was
okay, yeah, now it's timing out. So we're 1003, 1001, 9.98, 9.95, 9.92. Now I was assured that this would not hurt anything. I'm going to jumper across the 10x. Watch how quickly it starts counting down. See?
Yeah.
914, 910, 903, 876, 858. Now it resumes back to normal timeout. So if you have that thermal switch epoxy to a freeze plug and the engine's warmed up, you get an idea of how slowly it's timing out normally. And then when we connect this, it all of a sudden speeds up and starts taking off like a bat out of the, you know.
How'd that go again? How'd that go again?
So she just screaming on down there. It's supposed to take about 50 seconds to fully time out. Once this gets below 2.0 k ohms, I can switch the range on this and we can get a little bit more articulation. This is a 10K pot, which means every time it changes, it's changing by 39 ohms value. That means that when you're using an ammo box, every time you push an arrow up or arrow down button, you're changing the resistance value by 39 ohms. The 4X optimizers are going to have a 100 k ohm pot, which means that every time it changes, it's going to change by a value . Whoops. Yeah, that's better. Okay, it landed at 385 ohms on that circuit. So every change on a 10K pot is 39 ohms. On the 100K pot, it's a change of 391 ohms. So the 39 ohms, you can get your numbers pretty close, but the problem is that when you first start it up, you're only looking at 10K ohms. So it does create the possibility of cold start issues. So we went to a 100K pot so that it would reduce the chances of cold start issues. But because that's 391 ohms per step, chances are you may have to use the ammo box and adjust to a slightly higher temperature than you want. and then take resistors, and like we did on the board, go in there and splice in resistors just to bring it down a little bit. If you need more than 400 ohms of resistance, you got another step that you can hit on the ammo box. But you can micro-tune the 4X with resistors in between that 391 ohm jump that the ammo box will provide for you. Do you understand what I just said? Mm-hmm. Okay, so 385. Now, let's go off of here.
How big a resistor do you need to use to cover that?
Pardon?
How big a resistor do you need to use?
It's going to be less than 400 ohms if you got 391 ohms per step on the ammo box.
Amp-wise for size.
Quarter watt. Yeah, quarter watt. All right, let me see here. I need brown, I need orange. And now we're going to look at the oxygen sensor circuit. You guys remember that chart? This box is our oxygen sensor. This has a 0 to 1 volt range. So I'm going to start out at 0 volts. As I increase the voltage, when I get to 0.05 volts, remember, at 0.05 volts, it should go to about 0.35 volts coming out of the optimizer. See, it's 0.367 volts. So we just barely eclipsed our 0.05 mark. Now I'm going to keep on adding voltage, and if this one hasn't been changed, somewhere around 0.16, it'll trip to a high output, which is about 3/4 of a volt, 0.754 volts. Do you all see that? Now I keep adding voltage. I get up above 0.90 volts, and that goes to 0.90 volts. Oxygen sensor, normal operation is just up and down, up and down, up and down. So it's going rich, lean, rich, lean. But do you see how you're getting numbers that aren't either of the two? As I'm switching back and forth, 0.63, 0.46, 0.66, that wasn't any of the options. So I've had a question, well, my scan gauge is giving me all kinds of numbers, and none of them are the 0.35 or 0.75 volts. That's because it's going to extrapolate. There it says 0.367, and there it says 0.754. But just going back and forth like this, you see all kinds of numbers somewhere in between. So that's what you're also going to see in your scan gauge. Don't panic because the scan gauge is giving you all kinds of numbers, and none of them are the two that it's choosing from.
So it's switching faster than the scan gauge can read.
Yeah, it kind of extrapolates the voltage in there.
So it's just averaging them out.